All right, so the other day we left off with looking at the acetylide ion, which you'll remember hopefully is negative carbon that's part of a triple bond. All right, and so we did an example of a synthetic, a retrosynthetic analysis involving that. Let's try another one. All right, let's see. We can make this guy from compounds with 2 carbons or less. So this is sort of a new phrasing, a new kind of context that you'll see a lot of times in synthetic problems is, sometimes they give you a specific compound they want you to start with. Sometimes they just tell you to start with some generic pieces and put them together. Okay? So again, let's sort of walk through this one together. I'll give you another one in a minute. I'll let you try to figure it out by yourself. Well, again, first thing, let's take stock of what we have and what we're going for. All right? What are we going for? What type of molecule, first of all? What are we trying to make? A ketone. All right? So we kind of consider possible ways that you've learned to make a ketone. Also, remember, at this point, you want to start taking stock of your carbons, both before and after, right? You're looking to make a 4-carbon molecule from 2 carbon or fewer, so 2 or 1 carbon fragments. So that tells you at some point in here, you're going to need to have a carbon chain that you're going to extend, right? So this is all stuff, again, you can do before you even try to figure out any of the steps. It's a good way to get you started. Right? Now, that being said, take a look at this. And we can work forward or backward here. Does anybody have any ideas for how we get started?
Start with a 2-carbon alkyne.
Start with a 2-carbon alkyne, sure. Seems like a good place as any to start. We got a 2-carbon alkyne. And as you guys know, there's a few different things we can do with alkynes. What do you want to do with this one?
Yeah, I agree with
Uh-huh. Okay. So if we react it with NH2 minus, that's going to abstract a hydrogen. It's going to create an acetylide. Now what? What's the whole point of making an acetylide? Add carbons. So let's add some carbons. How many carbons do you want to add? 2? Sure. How do you do it? What do we add to an acetylide to get extra carbons? What's that? 2-carbon unit with halogen?
Yeah.
Okay, an alkyl halide. All right. You can definitely add an alkyl halide. And if you remember, basically what happens is just a good old nucleophilic substitution. So what that would do in this case is it would extend the carbon chain by 2 and give you a 4-carbon alkyne. Now, we got to figure out some way to get to the ketone.
reacted with HCl and H2 and so forth.
Need one more thing. Yeah, don't forget the HG, so forth, since this is a terminal alkyne. Yeah. So we need to create a carbon-oxygen double bond. You know, there's a couple of ways we can do that with an alkyne. We can do either a hydration or a hydroboration oxidation. We picked hydration here. Why did we pick hydration and not hydroboration oxidation? That also makes a C double bond. What would be the problem with doing a hydroboration oxidation of that?
Going in aldehyde.
Yeah, hydroboration oxidation would put the C double bond O in the wrong spot. It would put it on the end and make an aldehyde. Okay. So for that reason, you pick the hydration, and there you go. That is the entire synthesis, 3-step synthesis. Definitely, getting a little bit more complex, but again, you just figure out a step along the way until you get there. All right. Does that make sense? Are there any questions on how we got that one? All right. We'll erase this one here. I'll put one up here in just a second. I'm gonna let you guys work on it. Let me find a good one. Let me finish, right? I'll tell you when I'm done writing it because I'm sort of trying to adjust one in my head. That one turned out a little bit shorter than I meant for it to, but it's kind of interesting. Try that one. That's actually just a 2-step synthesis. But it's a little weird looking, isn't it? It's going to involve one old thing and one new thing. Give y'all a few minutes here to see what you can come up with. A few of you stopped working. So let's just go ahead and start discussing this one. All right, so I said it's 2 steps, right? What are, how do you want to start? How do you approach this one? Anybody have an idea for one of the steps? What's that? Halogenation of what? What's that? I'm sorry, I couldn't hear you. An alkene or alkyne? Yes, you need, first thing that you need to do is you're going to need to convert this to an alkyne. Right? You've learned one way of making alkynes, and that was way back in chapter 7. All right? How did we go about making alkynes? Do y'all remember? Anyway? What do we have to take away from these carbons in order to make an alkyne? What are these carbons losing? Oh, you guys got the deer in the headlights this morning. What's that? You're going to need to lose 2 hydrogens from this carbon. What else? Promise it's not a trick question. You need to lose both of those bromines, right? So basically, you're losing 2 HBRs, right? When you lose an HBr, that's called a dehydrohalogenation, right? So basically, you need to do 2 consecutive dehydrohalogenations. Right? And we learned about dehydrohalogenation back in, actually it's chapter 8, not chapter 7. Sorry. We need a really strong base, right? So there's a couple of ones we can use. Again, the amide ion works very, very well here, right? Definitely, if you don't remember that reaction, commit it to your memory because it's going to be a really useful one whenever you do syntheses, right? You can take a dihalide, do 2 consecutive dehydrohalogenations to make an alkene. Excuse me, make an alkyne. Then you look at this, right? What type of molecule is that? What do we call it? Tetrahalide, right? We've learned exactly one way to make a tetrahalide. How is that? Hydrohalogenation. 2 consecutive hydrohalogenations, right? So actually, no, you were right. My bad. Wrong thing on the brain. Yeah. We're going to do 2 consecutive halogenations. 4 bromines get added across the 2 hydrogens. Okay. Does that make sense? We got that? Are there any questions about how we went about getting this? All right. Let's try one more synthesis and then we'll move on. We'll make it a good one. All right, so we're gonna try to make that. Didn't leave myself much room here. Make this from at least one acetylene molecule, plus anything else that you need. Now that's an intimidating one, or at least an intimidating looking one. Do y'all remember what acetylene is? What is acetylene? What's that? It's basically ethine, yeah. CH, triple bond CH. All right, I'm going to walk through, I'm going to sort of talk through this one with you, because this one, again, is a little bit intimidating. You know that you have to start off with acetylene, so we have that. All right. Again, take stock of what you have and what you're trying to get. You have a 2-carbon alkyne, and you have a 1, 2, 3, 4, 5, 6, 7, 8, 9-carbon unit over here. That's a ketone, right? What should probably be the first thing in your mind that you know you have to do? Not necessarily the first step, maybe it is, but what do you know that you have to do? You got to add carbons. You got to add a whole lot of carbons, right? So we got to figure out how we're going to go about this. I think probably a safe assumption is that you're going to be taking this and making an acetylide out of it, right? Okay. So now you got to figure out where you actually want, or what type of alkyl halide you actually want to add. How many carbons do you want to add, right? And looking at this, it's not entirely obvious, right? What you should do is kind of look for little touchstones here. And I think one of the more important parts here is going to be that carbon-oxygen double bond, right? You have a carbonyl group. What type of molecule is this? What functional group? It's a ketone. Ask yourself, how have I learned to make a ketone?
Hydration.
Hydration of?
Well, for that one, it'd have to be an internal alkyne.
An alkyne, right? Yeah, an internal alkyne. Right, so that gives us a little bit of a strategy, a battle plan. We need to have a triple bond somewhere in here, either on this side or on this side, in order to hydrate. All right. Let's take a look at having it over here. Let's take a look at this unit over here, and let's see. I'm going to erase this and say, let's see what it would take to give us a 4-carbon alkyne. All right? How could we do that based off of what we've got going so far? How could we extend this carbon chain to 4 carbons? 2-carbon alkyl halide. And that gives us a 4-carbon unit with an alkyne at the end. Okay? And we've got a triple bond sitting there, which is good. We want that triple bond. All right? Y'all with me so far? All right. Now, we still don't have enough carbons, do we? Let's go ahead and add some more carbons. If we do this, again, to make another acetylide, we can extend our carbon chain again. And there's no limit to the number of carbons you could add at once. We could, in fact, go ahead and add this big old chain over here. And we will. So Really did not do a good job of leaving myself room, but that's okay. You could do that reaction. I'll put it down here. And it would give you that alkyne. Now, once you get there, it's easy. What do you have to do now? There's only one more thing that you have to do. Marissa, what did you say you wanted to do earlier?
The hydration.
Hydration, yeah. And if you hydrate this particular alkyne, boom, it'll give you the product that you want. Y'all see how we went about that? Yes, ma'am.
So for this, where we're extending it on both sides, it wouldn't matter which side we started on, essentially.
Oh, what do you mean? Like we're putting the alkyne group?
Like, so. Oh, I figured it out. Never mind. Don't.
Are you sure?
I think so. Yeah.
Or do you mean like start it going backwards or forwards or?
Well, like instead of like starting with the left one, instead you added the right one first. When
I mean, one thing, Marissa, that you'll find in all of you, you'll find out with synthesis, and this is, some people love it and some people hate it. There's oftentimes more than one right way to go about it. There's more than one pathway that can be correct. So you're thinking maybe, okay, instead of building the initial alkyne from here, maybe build it over here. Let's see. Yeah, you could do that.
Yeah.
I think it would be a little bit more trouble, but you could do it. Are there any other questions on this one? Do y'all understand how we got there? Anybody intimidated yet? I understand. Respect the chemistry, but don't fear it. It's entirely doable. You just got to do lots of practice and get one little bit at a time. You really like detective stories, you know. They like escape rooms. I love those things. Think of it like that. That's a good idea. An organic chemistry escape room. Ooh, you make an escape room and you have to solve organic problems to get the clues. I have to think about this. Everybody's like, oh, God, no. All right. One last little thing to talk about with regard to acetylide ions is, you know, we said that they can react with alkyl halides. It's not the only thing they can react with. They can react with epoxides as well. Yay, epoxides. Epoxides, they'll react with any, you know, moderately strong nucleotide. And acetylide falls into this category. So if you had something like this, and this is really not a new reaction. You've learned about reactions of epoxides back in chapter 9, how they can react with the nucleophile. The nucleophile comes in, attacks one of the carbons in the ring, breaks the epoxide open. And then you protonate the oxygen. Okay, the only thing that's new here is you're learning about a new type of nucleophile that can be used for these purposes. Otherwise, the same rules that you've already learned for epoxides take effect, right? If you had, you know, this, what would happen? What would that acetylide do? You guys are extra quiet this morning. Well, what did it do in the last one? Yeah, attacked one of the carbons in the ring. What's the only difference about this one as opposed to the last one?
To choose which one.
You got to choose, right? We didn't care last time. We just attacked one. So you have to make that choice. Remember, there's two different situations here. You got to figure, is it going to go after the more substituted or the less substituted carbon? Which one is it going to be here? Is it going to attack the more substituted or the less? Ooh, this sounds like a good time for a vote. Who says the more substituted carbon? Who says less? Pretty even on both sides. Let's see. Draw it extra slow for anticipation. I'm sure you're on the edge of your seat. Less substituted carbon. When do you attack the more substituted carbon in an epoxide? When the O is positive. Only when the O is positive. Since it's neutral, you attack the less substituted. Okay, not having the little edges of my board here is really throwing me off. Sorry. So you get that. So, ooh, that's intimidating looking. Imagine if you had to do a synthesis where you had to make that. Something with a triple bond and an OH. Well, guess what? You know how to do it now, right? You see a triple bond and an OH, probably tells you you're going to have to attack an epoxide with an acetylide ion. Okay? Does that make sense? Are there any questions about acetylides, alkynes, anything related to this chapter? All right, we're done with chapter, whatever this is, chapter 11. All right. So we're gonna sort of shift gears a bit here now and get into something that's definitely a little bit different. This is gonna be chapter 12. In chapter 12, it's all about redox reactions, oxidation reductions. We've done actually a few of these over the course of organic 1, right? Here and there. This was a sort of a concentrated chapter on redox reactions. Again, doesn't cover all of them in this chapter, but it covers a lot of specialized ones that don't really fit necessarily into some of the other categories. Okay? And you guys have been studying redox reactions for quite a long time now, right? I'm sure if you had chemistry in high school, you talked about redox reactions. So what happens during a redox reaction? Something gets blank, and something else gets blank. Fill in the blanks. What does redox stand for? Something's oxidized and something's reduced, right? So that's what we're going to see here. Something's going to be oxidized, something's going to be reduced. Now, let's review our definitions. What does it mean to oxidize something? If something's oxidized, what happens to it? What's that? Opposite. Loses electrons. And by process of elimination, you can probably figure out that reduction is going to be the opposite. Gains electrons, right? That's the definition of, those are the definitions of oxidation and reduction you guys have learned probably since like sophomore year in high school or something like that. Right? However, I want to expand upon these definitions because this doesn't necessarily tell the whole story as far as organic chemistry, as far as covalent molecules. When you say something loses an electron, I don't know about you, but to me that implies it loses it completely. It gives it away, right? And actually in the examples you saw in Gen Chem and in high school, that's what happened. It would tend, something would tend to give away an electron, or in the case of reduction, completely gain an electron it never had before. However, we're going to see redox reactions in which atoms initially have 8 electrons, and afterwards, they still have 8 electrons, but they've either been reduced or oxidized. That's because you don't necessarily look at it just in terms of absolute loss or gain of electron. You can look at electron density, and that's a phrase that I introduced to you guys early in Organic 1, right? We've seen that if you have a bond between 2 atoms, they don't necessarily share those electrons equally, right? If something's more electronegative, it'll pull some of that electron density towards it and have a greater hold on it, even though technically both atoms have some ownership, right? In oxidation of an organic compound, one of those atoms, when it's oxidized, tends to have less of a hold on the electrons than it did before. Does that make sense? Okay. And reduction is the opposite. Gains electron density. As an example, I'll draw a couple of different compounds here. I'll draw that. Yeah. And I'll draw this. And what I want you to do, I want you to look at each one of the carbons. I'm drawing a little box around. All right. Skeletal structure, don't forget, dictates that there's actually a couple of hydrogens on this one as well. So I'll go ahead and draw those so you can see them. That carbon that's in the box, how many electrons does it have? In its outer shell. It's got 8, right? 2, 4, 6, 8. What about this one? How many does it have in its outer shell? 8. 2, 4, 6, 8, right? So the same number of electrons. However, I can tell you, this is the more oxidized carbon here by far. Why is that one more oxidized? Yeah, this carbon right here has exactly 1 bond or 2 electrons shared with something electronegative, right? So it's sort of only losing its hold on this 1 pair. This carbon, however, has 1, 2, 3 bonds, 3 pairs of electrons that is kind of fighting with oxygen over, right? So the electron density on this carbon is lower than it is over there. So we would say this is a more oxidized carbon than that other one is. All right. Does that make sense? Are there any questions on that before we get into the heavy duty stuff? Oh, it's not heavy duty, just more substantive stuff. All right. There's another guideline that you can use to oxidation reduction, other than what I just put up. When something's in a more oxidized state, it tends to have an increased number of CZ bonds. Z just represents anything electronegative, right? And you saw that there. The more oxidized carbon had more bonds to electronegative oxygen. So you see more CZ bonds and or fewer CH bonds. And reduced is just the opposite of that. So this is one that doesn't have any electronegative atoms, right? We have ethane on the left side and ethine on the right side. However, one of these definitely is more oxidized than the other one. Which one of these two is more oxidized? The alkane or the alkyne? Yeah, why? It has fewer CH bonds than that alkane does, right? So there's a couple of different contexts that you can look at when you're trying to figure out what's more oxidized or what's more reduced or whatever. All right. So let's go ahead and start taking a look at some of these reactions. All right, and we're going to start off with reductions. All right, specifically when we're trying to reduce a particular atom or set of atoms, right? And don't forget what we just said. Whenever you reduce something, you tend to make more CH bonds. So basically there's three different processes or three different sets of reagents in which we can use to add more CH bonds to a molecule, all right? One way to do this is to add H2. That's just elemental hydrogen, H2 gas, in the presence of a metal catalyst. There's three catalysts that are commonly used: platinum, palladium, or nickel. This has a name. This process is called catalytic hydrogenation. Okay. So that's one. Another way to do this is to add two equivalents of sodium. And make note, this is elemental sodium. I guess I should really just put a little S over here. It's not Na+, elemental sodium. And also two equivalents of NH3, which is ammonia. You guys ever seen somebody put sodium in water? You've probably all seen that, at least on YouTube, or not in person. It's pretty cool. The sodium, whenever you do that, that sodium is being oxidized by the water. So it's in the process of giving up an electron. We can also use it for our purposes here. And the third way to do this is to add hydride. Hydride is a negative H. And there's a couple of different ways we can go about adding hydride. Sometimes we follow it up with a proton source. Sometimes we don't. There's just a couple of different situations. All right. right, so the first one we're going to talk about is catalytic hydrogenation. So I want to go ahead and just get you started in this one a little bit. Okay. Basically, what you use catalytic hydrogenation for is for hydrogenation of pi bonds. And you can do this with either alkenes or alkynes. Let me show you with alkenes first, because it's the simplest. So basically what you do is you take an alkene, you take some hydrogen gas, bubble it through in the presence of a metal catalyst, we'll just say nickel. And the end result is that both carbons in your double bond end up getting one of the hydrogens. Fairly simple, right? There is a mechanism for this. It's going to look kind of different because it's very much a physical aspect to this mechanism as well, in addition to the chemical. Your book has a much better diagram of this. So I'm going to, you should probably make a note to look at the book for this. I will attempt to draw this up here as well. All right, so what I'm going to do, I'm going to redraw this like that. And for the nickel, I'm going to draw this little surface. We'll just label it nickel over there. This little parallelogram that I just drew represents the surface of the catalyst, surface of the nickel catalyst. Basically what happens is when the H2 gets kind of close to the nickel, it kind of flutters by and this bond will break and the hydrogens will each sort of plant themselves on the surface of the catalyst. And this was like little hydrogen trees coming up. And if that helps you remember it, that's great. All right, you have your little hydrogen trees, and then your alkene comes fluttering by. And when it gets close enough, these can hop off. Remember, each one of the hydrogens has one electron. This double bond can split. One electron can join. With each one of the hydrogens. And that gives you your alkane. Again, there's a better diagram in your book, but that's kind of the best artistic version I can put up there. Okay, does that make sense? One important thing to note about this, not so important for this reaction, but it will be when we take a look at this reaction with alkynes. Catalytic hydrogenation happens via syn addition. The H's always come in from the same side. And that's why I made sure to kind of draw both of these coming in from the top side here. They always come in from the top side, or from the same side. Again, doesn't matter when you do it with alkenes, but when we do it with alkynes, that's going to make a difference in stereochemistry. All right, we are almost out of time. I'm going to be generous and give you guys 2 minutes of your life back today. So you're welcome. Are there any questions? All right. I will see y'all in lab. Have a good one. What's that?
I said my hands are struggling.
Oh, getting dry.